Hi class! So there have been a lot of questions about this question from the Chapter 17 homework, and I wanted to just walk you through it because it's worked out a little bit different than the other questions you've seen before. And so this is the question from Chapter 17 homework number 6. You probably have slightly different numbers, but probably the same compounds. So the question is, what is the mass in grams of each of the following soluble salts that can be added to 270 milliliters of 0.050 molar barium chloride without causing a precipitant form, assuming that there's no change in volume? So there are 3 different soluble salts here that we're going to add to it, and I'll work out all 3 because each of them have something a little bit different about how they're going to work out. So things to remember from Chapter 4. In Chapter 4 we learned about solubility tables, and we also learned about double displacement reactions. So the double displacement reactions are where they switch partners and the cation switches its anion out for the other one's anion and vice versa. So we have barium chloride as the first reactant in all 3 reactions. For this first reaction, our second reactant is ammonium sulfate. So when these 2 combine through a double displacement, here are the products. Barium leaves chloride and goes to sulfate. It would not go to ammonium because they're both positively charged. So we end up with barium sulfate, and barium and sulfate are both 2 charges, 2 plus and 2 minus, so it's just going to be 1 to 1. And the other one we're going to get is the ammonium is going to go to the chloride. Ammonium is 1 plus, chloride is 1 minus, so these are also going to be 1 to 1. So their formula would be ammonium chloride, NH4Cl. So in Chapter 4, we learned about solubility tables. Ammonium is one of those things that whenever it's there, it is always soluble no matter what. There's no exception to the ammonium rule, so this one's soluble. So it would not cause a precipitant no matter what the concentration is, pretty much, or at least to some degree. Barium sulfate, on the other hand, was one of the ones listed in the solubility tables as being insoluble. So back in Chapter 4, we just said it's insoluble, it won't dissolve, that's it. But now in Chapter 17, we learned that's not quite the case. When things are generally listed as insoluble, they actually do dissolve and dissociate to some small degree in an equilibrium reaction. I'm already moving my class online. No. So we get barium 2 plus, and we get sulfate 2 minus. And to find the equilibrium constant for this reaction, we would look it up in the table. So that was table 17.4 in the textbook. And the KSP for barium sulfate is 1.1 times 10 to the negative 10. Now, good news, no ice table needed here. The equilibrium expression here is going to be products over reactants. So our products are barium and sulfate, and they are 1 to 1, so they each have an understood power of 1. And sulfate, like that. And the reactant, this is a solid, so we ignore him, and that's all we've got. So now we're going to plug in what we know. So we know KSB, so we got that. Let me change colors real quick. We have KSB. Barium, how do we figure out barium? Well, if we are 0.050 mole of barium chloride, because barium chloride and barium are 1 to 1, there's 1 mole of barium in every 1 barium chloride. That means that we are concentration of barium ion is also 0.050 molar. So we got that part. So this is our unknown. So that's what we're going to solve for. So change colors again, and let's plug in what we have. Whoa, that was thick. Forgot to change the thickness. Okay. Control Z. 1.1 times 10 to the negative 10 is equal to, the barium ion is 0.050. And then sulfate ion is what we're solving for. Alright. So divide over here to the 0.050, and we get, for the sulfate ion concentration, 2.2. Right. So 2.2 times 10 to the -9. And so that is our concentration of sulfate ion. Alright, but the question doesn't ask what the concentration, it wants us to get to grams. So to go from molarity to mass, let's map out our plan. We don't have any way to go from molarity to mass, but we do know that both of these guys, molarity and mass, both can go to moles, right? Yay! When in doubt, go to moles. So from molarity to moles, we use the molarity equation. Molarity is moles per liter, which rearranges to moles are equal to molarity times liters. To go between moles and mass, that's where you use molar mass. The molar mass. So there's our plan of action. We've got molarity, we need to get to mass, and we need to go through moles. And in here we're going to have one extra step I'll show you, because we are at molarity of sulfate, but we want mass not of sulfate, we want mass of ammonium sulfate. Alright, so back to the problem here. So we're going to take molarity times liters to get to moles. So our molarity for right now, we're at the sulfate ion. 2 minus. So we found its molarity to be 2.2 times 10 to the -9 molar, times, now we have 270 milliliters, so 270 milliliters is 0.27. They didn't tell us how many SNO figures, so I'm just going to leave it at that, 0.27 liters. We've only got 2 SNO figures in the concentration, so we'll just leave it like that. 0.27 liters. 2. So 0.27 liters times the 2.2 times 10 to the -9 molar will give us, how many moles? 5.94. We'll leave an extra one in there for now. Moles of sulfate. Now, this is moles of sulfate. To get to moles, though, of ammonium sulfate, because that's what we need the mass of, we'll use the molar ratio. Now, I'm going to write it out this time. You're not going to really see that it changes anything because it's 1:1, but I'll just write it out because it's not always going to be at 1:1 for these other ones. So we're going to do this like a molar ratio, just like the middle step of 3 steps of stoichiometry. Moles of sulfate. 2 minus. Sorry, getting a little sloppy there. So here's our molar ratio. Sulfate goes in the bottom because that's what we're trying to get rid of. And we're trying to get to ammonium sulfate. So ammonium sulfate goes in the top. And H4, 2, and sulfate. 2 SO4. Now, in every ammonium sulfate, there is only one sulfate, so this is 1:1. So it's going to look like it didn't really change much of anything. That's fine. Sulfate's canceled. And so we're left with 5.94 moles of ammonium sulfate. So we're at moles. Last step is to get to the mass. So if we go from moles to mass, we're going to use molar mass. So molar mass, if you add up all your nitrogens, hydrogens, sulfurs, oxygens, it has a molar mass of, let's see, I wrote it down, 132.15 grams per mole. So let's multiply by that molar mass. 5.94. And when we multiply, moles are on the top versus the bottom, so moles cancel. We're left with grams, which is perfect. It's what we want. So our final answer should be for this particular problem. Oh, I lost my power. 5.94, that should have had times 10 to the negative 10. I'll put that in the editing so you don't get this far thinking I'm really not know what I'm doing. Alright, so then that leaves us with 7.8 times 10 to the negative 8 grams. And we are grams of ammonium nitrate, which is our final answer for part A. Ammonium sulfate, nitrate. Alright. I'm gonna make that look a little bit prettier for you. There we go. Final answer. 7.8 times 10 to the negative 8 grams of ammonium sulfate. So the idea, to recap what we did, the question is, what mass can we add that before we start causing a precipitant to form? So in our equilibrium, so we first determined what product would be an insoluble precipitant by using the switching partners, using the double displacement, and we found that barium sulfate was. We wrote the equilibrium expression for barium sulfate. We found the KSP for barium sulfate's dissociation reaction from the table. We knew that the concentration of barium, because we had 0.050 molar barium chloride, which is a soluble salt, and it's 1-to-1 stoichiometry between barium and barium chloride, so that was 0.5 molar. So we plugged that in and solved for what concentration of sulfate we would get. Now, this is at equilibrium, so at equilibrium is the most saturated this solution can possibly be. Any higher, and it would, if we increase this concentration any higher, it would push it towards being being more of a precipitant, going out of solution. In other words, it would push it back towards the product side. So Le Chatelier's principle says if you increase the concentration of one of your products, you push it back towards your product, and our product is solid. So that's where we're talking about by causing a precipitant to form. Increase this side too much, and you're going to push it back towards the solid, which is our precipitate. All right, so let's go on to part B. So I've done this one. Now let's look at part B. Oh, run away pen. Stop it. All right. Check. So lead nitrate is the next question. So just like with the first one, we're going to use double displacement to determine what are our two products for barium chloride reacting with lead nitrate. Now both of these are soluble salts. Barium chloride and lead nitrate are both soluble. But now barium is going to leave chloride and go to nitrate, so we get barium nitrate. Now barium, remember, is 2+, and nitrate is only 1-. So that will be Ba, and the nitrate, it will require 2 of them to cancel out the charges on the barium. Now the other one is going to be the lead and the chloride. Now lead, in this case, this is lead 2. If you weren't sure about the oxidation number of lead, since this is a transition metal, you can just check what it is bonded to. It's bonded to nitrate, which is 1-, and there's 2 of them, so this must be lead 2+. Chloride, Cl, is 1-, so it'll take 2 chlorines to cancel out. So the other product is lead chloride, lead 2 chloride, so 2 chlorines. Checking our solubility tables, barium nitrate is soluble. Nitrate is one of the solubility rules that has no exception. If it has nitrate, it's always soluble no matter what. Chloride is generally soluble, but it did have exceptions, one of those being lead. So this one is the insoluble one, so that is going to be our possible precipitant. And so we can write this as an equilibrium dissociation. So barium chloride dissociates and we form, lead chloride dissociates, we form lead 2+, aqueous, and I'm not writing the states of matter, but you know this is aqueous, and 2 chloride ions. And from our KSP table from chapter 17, we get that has a KSP value of 2.4 times 10 to the negative 4th. Alright, time to write our equilibrium expression. So products over reactants. So again, our products are lead, Pb, 2+, and chloride. So here's where I see most students mixed up. What do you do with that too? So from chapter 15, we learned if you have a coefficient, it becomes the power in your equilibrium expression. So that's the most common thing I see. Well, in this problem, pretty much, is forgetting to bring the coefficients down to your powers. Right. So let's figure out what we know. We know KSP, we just found that. We don't know lead, but we do know chloride. How do we know chloride? Well, the barium chloride. So up here we are 0.050 molar barium chloride. So if I am 0.050 molar barium chloride, now this is where it's a little bit different from the first one. That does not mean I'm 0.050 molar chloride. Why? Because of this 2. So if we put this as a molar ratio, you will get 2 chloride ions for every 1 barium chloride, right? So cancels. 0.050 times 2 over 1 tells us that we are 0.10 molar chloride ion. So that's what will go in here. And let's plug in what we know. 2.4 times 10 to the negative 4th is equal to our lead 2+ times 0.10 molar the chloride. Don't forget to bring down the square, squared. Alright, so I'm going to bring that over this side and divide by it. 0.10 molar, don't forget to square it. So 2.4 times 10 to the negative 4th divided by 0.10 molar squared gives us a concentration of lead ion of 0.024. Concentration of lead. Alright, so compared to the last problem, we are now here where we have our concentration, right here, have our concentration of the ion. So our next thing to go from molarity to mass was to go through moles, and using molarity is equal to moles per liter, or moles is equal to molarity times liters to get to moles. So we're going to do that again. So molarity, 0.024 molar, times liters, 270 milliliters, so that's still 0.27 liters, will give us moles, and that gives us 0.00648 moles of lead ion. Alright. But we're not being asked to find the mass of lead, we're being asked to find the mass of lead nitrate. So the next thing is to multiply those moles by the molar ratio to find moles of lead nitrate. Now, just like with the sulfate was 1:1, this will also be 1:1, so that's also going to be equal to the moles of lead sulfate, or lead nitrate. So 0.00648 moles lead nitrate. because it's 1:1. So last step, get from moles to grams, multiply by molar mass, add up the mass of lead, nitrogen, oxygen, and you get 331.22 grams per mole. Multiply across, moles cancel, and you're left with, in this case, 2.1. That's a pretty number. Grams of lead nitrate. Whew. So there is our final answer for part B. So this differed a little bit from part A in that you had a coefficient of 2 in our dissociation of the relatively insoluble, and so that changed things by having to make sure you brought down the square there. All right, one last thing is the part C. And the other thing that was different here was that because we were looking for the chloride ion, we also had to use molar ratio to get from the molarity of barium chloride to the molarity of chloride. All right, so on to part C. So check, check, on to C. So now we have sodium fluoride. So again, double displacement. Barium goes to fluorine, chlorine goes to sodium. So barium's 2+, fluoride's 1-, so that is barium with 2 fluorines. Sodium is 1, chloride is also 1, so that's just NaCl. Should hopefully recognize what that compound is. And hopefully you also are aware that that compound is water soluble. Salt does dissolve in water. Yay! Otherwise the oceans would be in trouble. Barium fluoride, on the other hand, is insoluble. So barium fluoride is going to be the one that we're going to have becoming a possible precipitant. So we will write its equilibrium dissociation. So when this dissociates, we get barium ions, 2+, and again, 2 fluorides. Like that. And the KSP value from that, from the table for barium fluoride, is 1.7 times 10 to the -6. All right. Equilibrium expression, products of reactants. So we have the barium ion, and we have the fluoride ion. And because there's 2, the fluoride ion gets squared. So what do we know? We know KSP. We know the barium ion concentration because I'm 0.050 molar barium chloride. That means I'm 0.050 molar barium ion because there's only 1 barium ion in the barium chloride. So let's plug in what we know. Change color just for change of pace. Let's pick something different. So our unknown now is the fluoride ion concentration. So to solve, we'll divide by the 0.050 molar, and that gives us 3.4 times 10 to the -5th is equal to the concentration of F. Do not forget that it is squared. Bring around the 2. Now at this point, because it's squared, but it's the unknown, to get rid of that square, we're going to take the square root of both sides. So that'll get rid of the square, so we're just left with the fluoride ion. And the square root of 3.4 times 10 to the -5th is 0.00583. So that is our concentration of fluoride ion. So to get from molarity to moles, we're going to multiply that by how many liters we have. Liters. Now, sodium fluoride and fluoride ion are also 1:1, so that means that's also 0.00157 moles of sodium fluoride. So last step, convert those to moles to grams by multiplying by molar mass. So molar mass of a sodium plus a fluoride is 41.99 grams per mole. Moles cancel, and we're left with 0.066 grams of sodium fluoride. So that is all three parts of this question. I know this video kind of went on long, but like I said, each of these had something a little bit different about them compared to the previous one. So for this problem, the thing that was a little bit different was that coefficient of 2 that meant it was squared, that was our unknown, which is why we had to take the square root of both sides here. So that was what was the big thing that was different with this one. So I hope this worked or helped you guys, and let me know if you have any questions.